Hey there, math fans. Going to talk about global max and min. These are questions in 3D calculus where we're trying to find the maximum and minimum of a surface over a given region. Students for years have told me they don't care for these questions very much because there are a lot of steps and it seems kind of daunting. I think they're pretty darn interesting, and I think they help you understand surfaces better. It's a simple principle. Yes, there's kind of if you have like a game plan, then you are going to be able to do this. I always tell people in like 10 to 15 seconds, you can lay out the structure of the problem. Yes, then you have to fill in a bunch of details, but the structure shouldn't be a problem. Basic principle here, and this is a picture of what's happening. And only recently I've been getting good at making these visuals. But the principle is the maximum is going to be above the edge. So ultimately, you're going to just draw the region. In this case, the region is this. And the maximum is either going to be above one of these edges. So this is like this edge here. Or somewhere inside. I guess that's not very much to say. So somewhere in here, above somewhere in here, or somewhere on the edge. Now there's too many points right now at this moment, and so we would like to reduce the number of things we need to try. It turns out that's pretty simple. So I tell students that ultimately you can immediately write down f of x, f of y. You're going to find when they're both equal to 0. And that's for the inside. That's to find out if the surface itself has any low points inside the region. Then you deal with the boundary, and that's the thing that's a little bit longer in 3D, but in this case, there's only two boundaries. There's this side, which is given by x squared plus y squared is 9. And there's the other side, which is given by x equals 0. Now, I think part of the confusion is that students are uncomfortable with regions. That's something you need to embrace. Come talk to me in office hours. We need to be able to label pictures and regions, especially have to do with parabolas and lines and circles. So you have this side, let's call it side A. And I often tell students, if you just write these things that I've written, you are already most of the way to the answer. Those are the 3 jobs I have to do. So yes, there's stuff to fill in, but it shouldn't be as daunting as people find it if they understand the ideas. So basically, we're going to study along this curve, around the edge. When is it biggest and smallest? And there's a lot of potential things, but we don't need to plug in every point. We do need to plug in the end points, the low points, and the high points. How do we do that? We restrict our surface to being above here. So we solve for either x or y, or we somehow parameterize it. In this case, I think it would be fairly easy to substitute in if we wrote it this way. And then we can get a 1 variable function. And that turns it into a 1 variable calculus problem. So I'm not going to do this here. I did this in class. I talked about this. And the biggest and smallest x can be is -3 to 3. How do I know that? Because it's a circle. And so this becomes a 1 variable calculus problem. So go back to your 1 variable calculus instructor and ask them how to do this. I also reviewed it in class. So you would need to figure out the maximum over that region, and then separately, you would plug in x equals 0 and figure out the maximum of this for y between, sorry, x, I said it wrong. First of many mistakes. X is from 0 to 3. I guess it isn't that easy. And y is from -3 to 3. Okay, so the 3 problems are to find the maximum of this, to find the maximum of this, and to see if there's any critical numbers. And at the end, you plug those in and find out. So there's these 3 parts. So here's my actual visual. I showed this in class. We're basically breaking it down and saying, okay, I just want to study that wireframe, so to speak. And that's what we're going to do. So some students tell me it's helpful to see that. In order to study that, you can't just plug in the corners. The corners are important, but you have to also find the bumps along the edge. Okay, so let's lay out the template for the next one. So this is the maximum, and this is a cool little wavy thing. But let's just lay out the pieces. So we're going to draw a circle, radius 2, 2, -2, and we know what to do. We're going to find the critical points inside the region. We're going to substitute in y equals 0. That's the bottom region. So at some point in this problem, we're going to need to study this. In this case, it's actually linear. So we're only going to have to plug in the endpoints. We do know the endpoints are -2 to 2. So there's a one variable calculus problem. And then we have the circle, the upper semicircle. So I could solve for y. Maybe I'll do it right now. Square root of 4 minus x squared. Substitute that in and study that. So I just think these problems are not as bad as, I think students see the solutions in the exam archive and they go, oh, these are terrible, but not really. So they're problems where you should get most the credit because you can write down most of the steps in a few moments. Okay, let's look at another one. That's this one we just talked about. Looks like if you saw the picture, you would say, well, the minimum is probably right there and the maximum's up here. But we're trying to give you a process where you don't have to be able to visualize it to do it. Let's look at two others. So right now I'm just talking about that setup. I feel like setup stuff is not a big deal. So let's look at a few other ones. Here's from an old exam of mine. Now, again, if you could see the picture, you would see that the max is here. And so this would be, less interesting. But what you do is you draw the region. It's y equals x squared. It's x equals 4. Done. And it may not be there. It might actually be here. I don't know, somewhere. What is our job here? We're going to do the partials with respect to x to see if the surface itself has any bumps in the region, set them both equal to 0 and solve. And unfortunately, we have three sides. We have y equals 0 as one side, and we're going to plug that into our surface, get a one variable function and analyze it. We're going to do x equals 4, plug that into our surface, get a one variable function and analyze it. And we're going to plug in y equals x squared. Get a one variable function and analyze it. That's the game. Let's look at another one. So again, you might have questions about, I just want to make sure that when I see students on their test just plug in random corners and then get frustrated they didn't get more credit, this is the stuff you should be doing. It should be clear on the page that you did this, that you knew to analyze the sides. All right, let's look at one last one. This is actually the one I did in class. And in my class, I actually reviewed how we do those one variable problems. This is the one I've been doing in class for quite a few years. It's above a triangular region. So the first step is to draw that. 0, 0, 0, 4, 2, 4. This one requires a little bit of initial startup because you need to find the equations for the side, but they aren't that bad. This is y equals 2x. If you need a review on how to find the equation of a line, I'm happy to do that. Ask me on the discussion board. Ask questions about everything you're mixed up on. But I have to also try to make this video fit. Okay, so what are we going to do here? The partial with respect to x, the partial with respect to y. You're going to set those both equal to 0 and solve. You also are going to have to study when x equals 0, what happens in my surface? When y equals 4, what happens in my surface? And when y equals 2x, what happens on my surface? And for each one, you're going to do a one variable calculus problem. So I just wanted to talk about that, sort of strip away the rest of the problem. All we're doing is walking around so that we can find, for the one variable calculus problem, where that point is. In terms of details, come ask me. But that's the structure of the problem, the structure we should know. All right, I hope that helps.